In this video, we introduce the difference between permutations and combinations. Let's get started. So remember, last time we talked about the fundamental counting principle, or the FCP. What did the FCP do? Well, it told us that we could multiply the number of possible ways for each selection to happen. For example, if you were choosing from a menu and you needed to select a drink, an entree, an appetizer, and a dessert, however many ways that there were to do each of those selections, we'd just multiply them together, right? And that would give us a total number of ways that we can make our menu item selections. Well, today we're going to talk about two types of ways to find out the number of ways that we can pick a subgroup of items from a total number. The difference will be whether or not order matters. So we begin with noticing that as long as there's no repetition of items, for example, if you were ordering from a menu, if you can't order the same thing twice, that would be no repetition, then one of these two possible items could be chosen as our method. We could either choose the combination approach or the permutation approach. Now, sometimes in English we misuse words. For example, you may have heard of a combination lock. Well, a combination lock, the order matters the order in which you enter your code matters, right? So technically, it should be called a permutation lock because permutations are when order matters. So I noticed in my chart here, if order matters and there's no repetition of items that we're choosing, we would call this a permutation. On the other hand, when order does not matter, we would call this a combination. So technically, when you're talking about passwords or locks of any type, combination would not be the appropriate tool. We'd use a permutation. Now, the way that we're going to find combinations and permutations, we'll follow a certain formula, and we'll teach you how to do that by hand today. But I also want to make sure that you're aware of, at the bottom of your slides in the interactive notes, whether you use the PowerPoint or the PDF version, you're going to find links to tutorials, YouTube videos, where someone is going to show you how to use the TI-84 graphing calculator or the TI scientific calculators in order to do combinations and permutations quickly. But I will show you by hand today in this video. Okay, so the combination formula says, I'll write to the side here, N choose R. So N is the total number of items that you're choosing from. R is the number in your subgroup that you're choosing. Would equal N factorial. Now, if you've never seen that before in math, the exclamation mark is called factorial, and it simply means start with that number. If n is 5, for example, start with 5 and then multiply it by the number 1 less, 4, and then 1 less, 3, and then 2, until you get to 1. So that's what the factorial does. Divide n factorial by whatever r factorial is, times parentheses n minus r factorial. So an example of this, you'll see on the screen, says imagine you had 6 people and you would like to know how many pairs you can make out of those 6 people, right? Maybe you're trying to couple people up, something like that. So here we notice that the order doesn't matter in which we couple them. So if Jin and Tom, that's the same as Tom and Jin. So order doesn't matter here. So if you want to know how many 2-person couples you could make or pairs you can make from a group of 6 people where the order in which you select them doesn't matter, we could use this combination formula. So to do it by hand, this would mean n is 6, so 6 factorial, over r factorial, where r is the number you're choosing from the group, so 2, and then multiply 2 factorial by the difference factorial, the difference of n and r. So 6 minus 2 is 4, so 2 factorial times 4 factorial. That sounds a little intimidating, but all that really happens when you do 6 factorial is 6 times 5 times 4 times 3 times 2 times 1. And so what that would yield is 30 times 12 times 2, or in other words, 720, which is what that numerator had. For its denominator, they got 2 times 24. Can you see why? Well, 2 factorial is just the 2 times the 1, so that's the 2 times the 1. But the 4 factorial would have been 4 times 3 times 2 times 1. So 4 times 3 times 2 times 1. Now, some things that some students do right now is they'll cancel through. For example, instead of getting 720 over 48, it looks like, for our denominator, you could have simply said that I noticed that 4 times 3 times 2 times 1 is on the top and on the bottom. So really, I just have 6 times 5, which is 30 on top, and 2 times 1, which is 2 on the bottom. Well, what's 30 divided by 2? That's right, 15. So another way of doing this is to simplify along the way. So what we're saying is, if you have a group of 6 people and you want to know how many ways you could pair them up, where order doesn't matter in the order in which you pick the people, it turns out there are 15 ways to do that. But what if order did matter, right? What if the first person that you picked for the group was going to be in charge of that group, and the second person would have to obey everything the first person said? Well, then the order surely matters. You want to know if you're first or second. That would be a permutation, or any type of situation where we're choosing a subgroup and order matters. So that's an example that you notice below. It says, suppose you have 6 people who are trying to compete for a contest. We want to know how many ways you could award a first place prize and a second place prize. So you're still just choosing 2 winners, but they're getting a different outcome. Maybe the first place winner will get a $50 gift card, and the second place winner will get a $25 gift card. The order matters here. So it's not a combination, but a permutation. Well, the formula is almost identical. I'm going to erase what we did a moment ago, so let's erase that screen. The permutation formula, right here, says for a permutation of n items where we are choosing r of them, order matters, we still would take our n factorial, that's the total number of items factorial that we're choosing from, divided by n minus r factorial, where that's the difference between your n and your r factorial. So again, if we're choosing from 6 items, we're choosing 2 people, 6 people, we're choosing 2 people to potentially win the contest, first and second place, but the order matters, right, because the places are different. This would still be 6 factorial on top and 4 factorial on the bottom. The only difference is we don't have r factorial separate, right? You can see that difference in the formula, in the denominator there. So we're expecting to actually get a bigger outcome since we're not dividing by that extra 2. So this turns out to just be 6 times 5 times 4 times 3 times 2 times 1 all over 4 times 3 times 2 times 1. You can see how tedious this could get, doing this by hand. So you might be thinking, is there a better way? Of course. Technology, like I mentioned, check out the links in the interactive notes, and you're going to see that there is a button on both scientific and graphing calculators that allows you to do a combination and a permutation almost instantly. But also you could use something called Pascal's triangle. Those are the same numbers, those ones on the edges and the numbers that we add up to in the middle. Those are the same numbers you get for your combination formula. So there are other ways, but for this class, I would recommend that you just use your calculator for this part so that you can just focus on the word problem itself. So 6 times 5 does give you the 30. So the answer to that question would be 30. There are 30 ways that you could select a first place winner and a second place winner, where order matters, right? They're different outcomes, for 6 people in this contest. Okay, so what I would recommend strongly is to pause the video at this point, check out those YouTube videos for whichever calculator you plan to use, and make sure you know how to get the permutation and the combination that we just did, but using your calculator to save time. So let's head over to our next example when you're ready. Example 1 officially says, determine if you would use a permutation or a combination. So what I care about more is, can you figure out which of these you're using, not can you do the arithmetic, right? You can use your calculator for that. So in part A, it says, the number of ways to select 2 markers from a collection of 8. All right, so I look in my marker bag. If I'm teaching in person, I might have 8 markers in my bag. I randomly pull out 2 without looking. What I'm asking here is, how many ways could I have done that? Now the question you want to ask yourself is, am I repeating any markers? No, so there's no markers that I'm going to put back in the bag, right, and repeat again. The second thing you want to ask yourself is, does the order in which I pick the marker matter? Right? If I pick 2 markers, does it matter if the first one's blue and the second one's purple, or vice versa? Not really. It just matters which 2 that I picked, right? The same would apply if you had 8 kids and you're choosing 2 of them to go to Universal Studios, right? Do they care if they're picked first or second? Maybe for bragging rights, but for the actual purpose of going to the park, they care about whether or not they got selected, not which order they got selected in. So when order doesn't matter, we would use a combination. So that would be the answer here. And if you want to practice and see, okay, well, how many ways could that happen? You would do 8 combination 2 using either the formula that we just did on the last slide or using your calculator. Now for the next part, it says, what if you were choosing let's see, it says we're choosing to arrange a 3-track playlist from 12 songs. So maybe you're having a party of some type and you would like, or you're studying and you want a certain soundtrack, right? And you would like for 3 songs to play, but you have 12 to choose from. Here again, you're not going to repeat any songs. We're assuming there's no repetition. So permutation or combination would make sense. But the question you need to ask yourself is, does the order in which I pick my songs matter? Well, for a soundtrack, yeah. If you're listening to a song first, second, or third, maybe this is your workout track, right? The order in which you listen matters. So since order matters, we would say this is a permutation. Okay, so again, if you were trying to figure out how many ways you could do this, N, P, R, in this case, 12P3. And you could put that in your calculator or into the formula that we learned. All right, let's practice getting some of these answers in our next example. Example 2, suppose you have 20 members in your club. Question A says, find the number of ways that you could choose 3 officers to form a task force for something, right? The question you ask yourself again is, can I repeat? Well, no, once you pick someone, you've picked them. You're not going to put them back into the pile, right? They're either picked or they're not picked. So no repetition, so permutation or combination is your choice now. How do you pick? Based on order. So you ask yourself, does the order matter in which you are picked to be on this task force? Well, how would you figure that out? The question that you need to ask yourself internally is there a difference in outcome, right? If you get picked first, second, or third, am I having different responsibilities? Does something different happen, or am I on the committee either way? In this case, it doesn't specify any differences. So you just want to know if you're on the task force or if you're not. This would be a combination. So since it's a combination, we could use our combination formula by hand or in our calculator. This time we're choosing from how many items? 20 people, that's right. And we're choosing how many officers? 3, good job. So if I was doing it by hand, the formula went n factorial, feel free to look at your notes, or you could pause it and try it yourself. N factorial is the bigger number, so 20 factorial, over n minus r factorial times r factorial. So 20 minus 3 is 17, so that's 17 factorial. And the r factorial would just be 3 factorial. Again, the order doesn't matter for multiplication, so feel free to put the 3 or the 17 factorials in either order. What I notice here is interesting is that 20 goes all the way down to 1, right? But 17 all the way down to 1 is in the denominator. So technically, what would be left in the numerator after you cancel? Yeah, that's right, just 20 times 19 times 18, and then 17 all the way to 1 cancels with the 17 all the way down to 1 in the denominator. That's pretty awesome. So that's where that 17 factorial, it canceled with the 17 factorial next to the 18 there. But 3 factorial is just 3 times 2 times 1, or 6. So 2 ways to go about this if you're doing it by hand, which is why I recommend a calculator because it can save you a lot of time. One way is you could just cancel right now. I, for example, know that 3 goes into 18, doesn't it? 3 goes into 18. How many times? 6? Yeah, that's right. 2 goes into any even number evenly. So 2 could go into the 20, for example. It doesn't matter which one I pick. And I'd get an answer of 10 in the numerator. What does that leave me with? Well, it leaves me with 190, 10 times 19, times 6. So my answer in example 2a here should be 1,140. So 1,140. This is the number of ways that you should be able to select a 3-person task force from 20 members in your club, okay, assuming that the order did not matter. Now take a look at B with me. The number of ways to choose a president, vice president, and treasurer. Now this time you're still selecting how many people? That's right, 3 people. But does the order matter? Well, yeah, because the first person you pick is the president, right? That's a little more powerful than a vice president. If you're like me, you'd rather be the treasurer. You don't have to go to as many meetings, okay? But you want to definitely know which position you got, so the order would matter. So if order matters, we would call this you got it, a permutation. So we would use a variation of that formula, so it's one less step, really. The permutation formula, NPR, said, in this case, 20 is our N, right? P, and we're choosing 3, president, vice president, treasurer, right? So the formula said take n factorial, so 20 factorial, over n minus r factorial. That's just 17 factorial, isn't it? Now this one's kind of interesting. You don't need the r factorial for the permutation in the denominator. So what really happens is 20 times 19 times 18 times 17 all the way to 1 will end up just becoming 20 times 19 times 18, because 17 all the way to 1 is in the denominator as well. They cancel. Let's think about why this makes sense. It's kind of like your FCP. Remember from our last section? We talked about the fact that the first item, when you make your first selection, if order matters, you could use the FCP there. You'd say there's 20 people to choose from. Well, once you've chosen one of them, how many are left to make your second pick? 19. If you've ever played team sports and they're picking people to be on the team, you know how this happens, right? One person gets picked and now there's one fewer to pick from, right? So there's 19 people for the second pick. And now they've taken that person out. How many are left for the third pick? Yep, that's right, just 18. So if you multiply 20, 19, and 18 together, that's the same result. So that's basically the FCP whenever we have a permutation like this. And so the end result there is a lot bigger. We end up with 6,840 ways. So there are a lot more ways to pick items or people to be in your subgroup when order matters. Because what you're saying is picking Sue, John, and Tom is different than picking Tom, I forgot their names already, Sue and John, something like that. The order mattered here because they had different positions. And so for each new grouping, that's a new way of selecting. Okay, so we've practiced in this example how to determine whether you're talking about a combination or a permutation. The key difference, does order matter? Okay, we're going to head off to our next example and see if we can continue figuring out which is which. Example 3. It says a certain state allows for its drivers to select 3 letters from the English alphabet, A through Z. By the way, that's 26 letters, so that's what we're choosing from, a pile of 26 letters. Followed by 3 digits, 0 through 9. Careful there, if you start with 0 and you end at 9 inclusively, that's really 10 numbers. So we have 10 options for our digits, 26 options for each letter. Okay. They say we're allowed to choose 3 letters followed by 3 numbers, 3 digits. It says how many unique license plates could be generated statewide. And here they give us our 2 different scenarios. Now you might be thinking, why would I have 2 different scenarios? Well, depending on whether or not you allow the driver to choose a license plate where the letters and numbers are repeated or not, right? If they're repeated, you have more options potentially. And if they're not repeated, you would have fewer options potentially. So we notice here, if repetition is not allowed, then what we're dealing with is either a permutation or a combination potentially. If repetition is allowed, we can't use a permutation or a combination. You can go back to our first slide. We would have to use the FCP, just multiply the number of ways together. So let's do the FCP for both of them, and then I'll show you how we could have also done a permutation. Why a permutation and not a combination? Because the order of your license plate matters, doesn't it? Yeah, so that's why it would be a permutation over a combination. So if we did the FCP approach first, what I would recommend, again, is a little slot for each selection. So I'm first choosing, it looks like, a letter. I'll use L for letter, if that's okay. Then I'm choosing another letter, followed by another letter. It said choose 3 letters, followed by 3 digits. I'll use D for digit. So D, D, and D. Now, technically, it's the exact same setup for the FCP in Part B, so I'll just go ahead and do that now. A letter followed by a letter, followed by another letter, followed by 3 digits, D, D, D. So let's just set it up for ourselves here. Now, feel free at this point. I kind of helped you a lot at this point. So feel free to pause the video and fill in these blanks according to what you remember from the FCP, because this is nothing new. This is from our previous section. Okay, let's see how you did. In the first case, if you're saying that repetition is not on the table, it's not allowed, that would mean that after you pick your first letter, and we had 26 possibilities for each letter, A through Z, how many choices would be left for your next letter once you've already picked one, assuming you're not allowed to repeat it? That's right, only 25. And then 24 for the third letter. Okay? On the other hand, if repetition was allowed, then for the first letter you have 26 options, but you still have the same 26 options each of the 3 times, don't you? So that's going to be a bigger number when you're allowed to repeat those letters. In other words, you're going to have more license plates possible. So depending on your state's population and how many drivers you expect per household, you might want to allow repetition if you have a bigger state with more drivers. All right, what about the digits? Well, there were 10 possibilities, right? We had, for the digits, 0 through 9. So that's 10. But then if I'm not allowed to repeat in Part A, 9 and 8. If I am allowed to repeat, what do you think? 10, 10, 10. Very nice. So the difference here, if you multiply this out, feel free to do it on your calculator yourself and pause and see if you're right. The answer I got for the first case was 11,232,000. That's how many license plates would be possible, assuming we followed this protocol, 3 letters followed by 3 numbers, digits 0 through 9, letters A through Z, where you're not allowed to repeat anything. But if we were allowed to repeat, we're expecting a bigger outcome. And sure enough, 26 times 26 times 26 times 10 times 10 times 10 should give you about 17,576,000. Okay, so that's a lot more license plates possible. So if you have a bigger state, this probably wouldn't even work for Florida necessarily, right? But if you had a big enough state, you would want to have repetition as an option. Another thing that you could think about if you were designing this scenario for yourself in your own little area that you control, if you're the mayor of the world or the governor of the world, or whoever makes these decisions, right? You could say, well, I'm going to allow a letter or a number, right? As soon as you do that, now not just 26 or 10, but 26 plus 10, you'd have 36 possibilities. And that would greatly impact the number of license plates allowed. Okay, what I wanted to show you though, before I move on to our next slide, I wanted to show you that we could have also done this part A with the permutation because order was important, right? So what would the permutation have been? Well, you would need a permutation of the 26 letters, and how many of the letters are we choosing? 3. Well done. And, which means multiply, we would need a permutation from the digits, right? Which were 10 digits, choosing where order matters, permutation P. We're choosing 3 of them. And it turns out that if you use your calculator or the formula, you would end up for 10P3 with 10 times 9 times 8. And for 26P3, you'd get 26, 25, 24. So you'd get the exact same answer. So I wanted to show you there's 2 approaches to that same problem that would get you the correct number of license plates. Okay, again, why could we not use a permutation or a combination for B? Yep, because with permutations and combinations, we assume we're not repeating anything. And that's why the FCP is the only way to handle a problem where we are allowed to repeat. So that might be something to put in your notes. Let's head over to our next slide here and see how we're doing. Example 4 says, this is a really important one for your future problems in probability, next section. How many 5-card hands of poker are possible from a standard 52-card deck? And I wanted to remind you what a deck of cards looks like if you're not a poker player, right? So in a deck of cards, again, there are 52 cards because there are 4 suits of 13 each. You have the black spades, the black clubs. You have the red hearts and the red diamonds. And in each suit, you'll have an ace, which could be interpreted low as 1 or high, sometimes I believe as 11. It's been a while since I played cards. But 2 through 10 are your digits, not really digits, but they're your numbers, your numerical numbers. And then you have 3 cards which have a picture of a person and a letter. Those are called face cards or picture cards, the jack, the queen, and the king. So that is what makes up a deck of cards, a standard deck of 52. So what they're asking me here is, how many ways could you choose a 5-card hand from a standard deck of 52? The question that you need to ask yourself first is, am I allowed to repeat cards? Well, think about if you were actually playing a game of cards. If someone gives you 5 cards, are they giving you a card and then putting it back and then repeating it? Or are you just getting a card and holding on to it? The latter, right? You're getting a card and you're holding it. So that means you're not repeating the cards that you're getting. So that's the first thing. There's no repetition. So the next thing is it a permutation or a combination? Well, does the order matter in which you get dealt your cards? Well, maybe on the game it depends, but if you're all getting your 5-card hand to begin with, it doesn't matter if you have an ace, a 2, a 3, a 4, or 5 in a different order. You just care about which cards are in your hand. So the order does not matter when you're talking about how many 5-card hands there are. So we would say this is a combination of 52 cards, and how many am I choosing in my hand? I'm choosing 5. So feel free to use your calculator to do this. This would be a big one to do by hand, the arithmetic. If you were doing it by hand, this would be 52 factorial. And then you do 52 minus 5, which is 47 factorial. And then you'd have to do the r factorial as well, which is 5 factorial. And when you calculate all of that out by hand and cancel everything, you will get 2,598,960. In fact, you could Google that to check, right? Type in your Google, if you have time and you're curious, how many 5-card hands of poker are there? That will be your total every time. So you'll see this number a lot when you start doing probability questions in your next section, where they say, what is the probability of getting a royal flush or getting 3 kings and 2 queens, things like that. The denominator will always be the total number of ways this could happen. This will be your denominator anytime you have a 5-card hand of poker. So keep that in mind. You'll be seeing that number a lot. All right, well, there's one more topic that we need to cover in this section. Let's get to it. It's the idea of choosing duplicate items. Here's what I'm saying. Suppose that you had a word like the word car, C-A-R. Pick any 3-letter word for the sake of my little example here, okay? Now, notice that I picked a word that had unique letters, distinct letters, C, A, R, they're not repeated, okay? If they're distinct, then if I asked you, how many ways could I rearrange these letters? Now, it doesn't have to form a word that makes sense, just rearranging them as placeholders. You could also not just think of words, but people, right? If you had Joe, Bob, and Sue, how many ways could you rearrange those three people? It's the same question. So as long as there's nobody being repeated, there's no letters which are the same here, here's what we would do. We could think, well, order matters, so that's a permutation, right? So technically you could say, oops, I think I clicked on the wrong thing here. Let me go back. There we go. Technically we could say P, because order matters, permutation, and we're choosing from 3 letters, and we're choosing all 3. So you could do P3, 3P3, that's hard to say in a hurry, 3P3, and that would end up being something like 3 factorial over 3 minus 3. Well, that's 0. Now, we haven't talked a lot about 0 factorial, but it turns out that's just 1. It's a definition. You can write that down if you haven't seen that before. 0 factorial and 1 factorial are both always equal to 1. So this would just be 3 times 2 times 1 over 1, or just 3 times 2 times 1, which is 6. But there's a faster way to do that, just using the FCP, right? For the first selection, you have 3 options, C, A, or R. Once you've picked one of them, now for the second option, you only have 2 letters, right? And finally, for the third option, by default, you're down to that last letter. 1 letter left. And there is 3 times 2 times 1, or 3 factorial, which is also known as 6. So yes, there would be 6 ways possible to rearrange the letters in the three-letter word car, okay? Same thing applies if you had 3 friends and you're sitting in a movie theater and it's Joe, Sue, and Kim, and you want to know how many ways you could rearrange them. There would be 6 ways to do that because the order matters, okay? But what if those 3 letters in this case had some that were duplicated? Well, there wouldn't be as many ways to rearrange them, would there? Let me show you what I mean. Consider the word wow, or dad, or Bob, or any word that has maybe a couple of repetitions here. So let's do wow for right now, okay? If I wanted to rearrange those, I could do W, I already have W-O-W, that's one way, right? But I could do W-W-O. What else could I do? Well, I could move the O, couldn't I? Yeah, put it in front, O-W-W. Well, can you think of any other ways I could rearrange those letters? For car, there were 6 ways, right? C-A-R, C-R-A, A-R-C, A-C-R, R-A-C, R-C-A, right? 6 ways. But for wow, there's only 3. So how do we account for that with a formula? Well, down here, technically, that's the way we do it, but I want to show you how this works. You say, first of all, how many letters were there? That's right, there were 3. So you start off with your 3 factorial. That's what it normally would have been had there not been any which were repeated. But now we're going to divide out by those duplicate items. So the duplicate items were, who were my duplicate items? The letter W, good job. So the duplicates are going to go down here. So the duplicate item W, how many times did it occur? Yep, twice. So I'm going to put 2 factorial in my denominator. For each duplicate item, you're going to put that number of times it occurs, I should say, factorial. So let's see what this looks like when we work it out using our little formula here. We would get 3 times 2 times 1 for our numerator, and for our denominator, just 2 times 1. Well, you could multiply it out first, or you could simplify it first. You know me, I like to simplify first. So I'd probably say 2 times 1 would cancel, and I just have 3. Or if you're someone who wants to multiply first, you would get 3 times 2 times 1 is 6, and 2 times 1 is 2, which eventually is still 6 over 2 is 3. Right? Same thing. So there's our 3 ways that we could rearrange those letters. And why there were only 3? Because we had the the duplication of the 2 W's, that's why. Well, let's try it with a more complicated word before we end this video. Do you remember back in our logic chapter, we had a big old word called tautology, yeah? It's not trilogy. I see some people write that on their test during Star Wars movie season. It's not trilogy. What is tautology again? Yeah, that's right. It was a statement which was always true. Okay, so suppose we had the word tautology. I'm not going to judge your spelling skills, so I've written it out for you here. T-A-U-T-O-L-O-G-Y. So you have the word tautology. How many ways could you rearrange these letters? Again, you don't have to form a new word, just how many rearrangements could there be? I would encourage you at this point, pause and try it yourself. We just did a 3-letter word a second ago. Could you do this word now by yourself? Okay, so come back and see how you did. Well, let's see how many letters there were. 1, 2, 3, 4, 5, 6, 7, 8, 9. So if there are 9 letters in the word tautology, we would begin by saying 9 factorial. And that's the answer, as soon as you work it out, of course, or use your calculator. That's the answer if there are no repeated letters, right? But are there any duplicate letters? That's right, there is a T that happens twice. Let's see if I can get that. There we go. T happens twice, so in the denominator, I need to write 2 factorial. Are there any other duplicate letters? Okay, so A does not duplicate, but O does. There's an O, there's an O. So let's divide out by that duplicate factorial, 2 factorial again. Anything else? No, G, L, Y, those are unique, aren't they? The U is unique as well. So our answer should be, when you work it out, 9 times 8 all the way down to 1. So 9, 8, 7, 6, 5, 4, 3, 2, 1. Times, that's 2 times 1, not 21, times, divided by 2 times 1 times 2 times 1. Some students get a little nervous when they see factorials next to each other. You just multiply those numbers together. So in the end, when you do all of the math and you simplify, you should be getting a grand total of 90,720 ways. So that would be the number of ways that you could rearrange the letters in the word tautology. And again, that would have been much bigger had we not had repeated letters. So if we had a 9-letter word with no duplicates, it would have just been 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. That's the number of ways that you could rearrange 9 items where order matters and nothing's been duplicated. Okay, so this was quite a bit today. In this video, you've now learned the difference between a permutation and a combination. With technology, you're going to save some time in doing those calculations, and you've also learned how to reorder the letters in a word by using permutations and factorials. I hope this helps. Remember, you got to practice because math is not a spectator sport. I'll see you next time.